this movie, we answer this question about a Faraday's law calculation, using it as an opportunity to understand the factors which affect electromagnetic induction, particularly the concept of magnetic flux and its relationship to the angle which a conducting coil makes to a magnetic field. Download the question from the link below and try it yourself first. And did you know that you can find many resources to help you learn natural and physical science on my website, www.learnscience.coza. Also, don't forget to subscribe to my YouTube channel. As I said, this question is about Faraday's law. What is that? Faraday's law describes how various factors affect the magnitude of the EMF that is generated when a conductor cuts through magnetic field lines. In other words, experiences a change in magnetic flux. Before we get to the calculation itself, let's quickly speak about this concept of change in magnetic flux. First, what is magnetic flux? We know that a magnet has an invisible magnetic field around it. Here we have two magnets with opposite poles facing one another so that their invisible magnetic field lines combine to be straight lines between the two magnets. Let's simplify the diagram like this. Here we have a piece of conducting wire bent into a rectangular shape, which we will call a coil. Now we place this coil into the magnetic field between the two magnets. Let's start by placing the coil like this, and let's view our diagram from different angles. Notice that many of the field lines pass through the inside of the coil. We say there is a high magnetic flux linkage with a coil in this orientation. Magnetic flux is a measure of the total magnetic field which passes through a given area. In this case, the area that we're interested in is the area bounded by the conducting wire of the coil. And we can see that in this orientation of the coil, we have many field lines passing through this area. But what happens to the magnetic flux when we rotate this coil? Here we can see the coil rotated a bit. What do you notice about how many magnetic field lines now pass through the inside of the coil? Fewer than before. The magnetic flux linkage with the coil has decreased. And now let's rotate the coil even further. Can you see that the magnetic flux linkage with the coil has decreased even more to 0 now? No magnetic field lines now pass through the coil's inside area. Whenever a conducting coil experiences a change in magnetic flux like this, then an EMF, an electromotive force, is generated across its ends. Generated means created, made. We could also use the word induced. Induced means caused to be made, caused to be generated. An EMF is a type of potential difference, a voltage, which pushes charges so that if there's a complete conducting path, electric current flows. What determines how strong this induced EMF is? The rate at which the magnetic flux linkage changes. Change the magnetic flux linkage with a coil more rapidly and you get a higher EMF generated. And that is what Faraday's law says. The magnitude of the induced EMF across the ends of a conductor is directly proportional to the rate of change of magnetic flux linkage with the conductor. We can give Faraday's law in equation form. EMF, measured in volts, is directly proportional to the rate of change of magnetic flux linkage. Rate means per time. Change in magnetic flux linkage means final magnetic flux linkage minus initial magnetic flux linkage. We use the Greek letter phi as the symbol for magnetic flux linkage, and it's measured in Weber. So rate of change of magnetic flux linkage is measured in Weber per second. But how do we calculate the rate of change of magnetic flux linkage with a coil of conducting wire? And how do we calculate the induced EMF? To understand how to do that, we need a way to describe these different orientations of the coil relative to the magnetic field. How do we do that? We imagine the area inside the coil as a surface. Then we imagine a normal line perpendicular to that surface. Then we measure the angle between that normal line and the magnetic field lines. So can you see that in this position, where the coil has maximum magnetic flux linkage, the angle between the coil's normal and the magnetic field is 0 degrees. Then here, where the coil has 0 magnetic flux linkage, the angle between the coil's normal and the magnetic field is 90 degrees. So we get full flux at 0 degrees and 0 flux at 90 degrees, and something in between for angles between 0 and 90 degrees. So the angle the coil makes to the magnetic field affects the magnetic flux linkage. Other variables also affect the magnetic flux linkage. The bigger the area of the coil, the greater the flux linkage if all other variables are constant. The stronger the magnetic field strength of the magnets, the greater the density of magnetic field lines, and so the greater the magnetic flux linkage if all other variables are constant. This equation summarizes all the variables which affect magnetic flux linkage. Magnetic flux linkage, phi, measured in Weber, equals the strength of the magnetic field B, measured in Tesla, multiplied by the area of the coil A, measured in meters squared, multiplied by cos theta. Why cos theta? Remember that we get full magnetic flux through the coil at 0 degrees and 0 magnetic flux through the coil at 90 degrees. This matches cos 0 equals 1 and cos 90 degrees equals 0. So let's say we rotate a coil from 0 degrees to 90 degrees. That changes the magnetic flux linkage with the coil. If we know the magnetic field strength of the magnets and the area of the coil, we can calculate the change of magnetic flux linkage with the coil. If we know the time taken to make that change, we can calculate the rate of change of magnetic flux linkage. From Faraday's law, we know that that is directly proportional to the EMF generated across the ends of the coil. How do we change the proportional relationship to an equality so that we can actually calculate the induced EMF? To do that, we need to understand the influence of the number of windings in the coil on the EMF. If instead of just having one winding in our coil, as shown here, we wind the conductor around many times, each winding in the coil has its own area which is penetrated by magnetic field lines, in other words, which experiences magnetic flux linkage. And so, it also experiences the calculated change in magnetic flux linkage. So the total effect of the rate of change of flux linkage of the whole coil is magnified by the number of windings in that coil. And that brings us to this equation. The EMF induced is equal to negative n, which is the number of windings in the coil, multiplied by the rate of change of magnetic flux linkage with a coil. Why negative? This negative refers to direction, an EMF direction such that it opposes the change which induced it. That's something I focus on in another movie. But now, back to this question. we need to calculate the change in magnetic flux if the coil rotates from 0 to 90 degrees. We know that that means that the flux changes from maximum to 0, so there's a decrease in flux. So the change in magnetic flux will be negative. We're asked to find out the change in magnetic flux of this coil, which means the final magnetic flux minus the initial magnetic flux. Magnetic flux is calculated as B, which is 2,5 Tesla, and that's not changing between final and initial, multiplied by A, area, here we have it, and that also is not changing between the initial and the final states, multiplied by cos theta, and that is changing because the angle changes from 0 degrees to 90 degrees during this rotation. So, of course, we could write this as all of this for the final minus all of this for the initial. But since B and A are constant, we can simplify this and simply write that that is equal to BA, which remains constant, multiplied by cos theta final minus cos theta initial. So let's substitute our values in. 2,5 Tesla multiplied by 2,8 times 10 to the power minus 3 meter squared multiplied by cos 90 degrees minus cos 0 degrees. Now you have to be careful with your calculator work here because of the BOMDAS rule. If you put it into your calculator without being careful of the use of the brackets, then what will happen is that this part will be done first, and then it will subtract this part. So this has to be done first, and after that's been done, then this part. Now, we could just maybe safeguard everything by doing this part in our head. I mean, we know that cos 90 degrees is 0 and cos 0 is 1. So we know that this is minus 1, and then that simplifies everything. If you don't want to do it that way, it might be safest to start with what's in the bracket. So we write cos 90 equals, and you see it's 0, minus cos 0. And you can see that gives minus 1. Then we multiply that by 2.5 multiplied by 2.8 times 10 to the power minus 3. And our answer is minus 0,07, or if you want to give it in scientific notation, 7,0 times 10 to the power minus 3. And what are we speaking about? Change in magnetic flux. What is magnetic flux measured in? Weber. What does the negative mean? Decrease. Which makes sense because initially the angle was 0 degrees. So there was maximum flux. Finally, the angle was 90 degrees where you get 0 flux. So from initial to final, there's been a drop in flux, a decrease. That's why it's negative. Now we're asked to calculate how much time that rotation must have taken. If the EMF that it induced is 3,5 volts and the number of windings is 200. So the unknown value is not already the subject of the formula. So that adds a little bit of complexity with the algebra, but otherwise it's really very easy. We've already calculated the change in magnetic flux linkage. This I copied down from the previous question. So we simply need to substitute that in there. This one we don't know. We know the number of coils and we know the EMF. So let's simply substitute. 3,5 volts is equal to minus 200 times minus 7 times 10 to the power minus 3 Weber is the change in magnetic flux. and we are trying to find out the period of time that that took. If your algebra is very good, you could just do that in one step, solving for delta t, but maybe for safety, let's rather break it down into more than one step. 3,5 is equal to, let's multiply these two. We know that minus times minus is plus. 200 times 7 times 10 to the power minus 3. And that is divided by delta t. So now delta t needs to be the subject of the formula. How do we do that? Well, one way is to multiply both sides by delta t and then divide both sides by 3,5. Or else you can see this as a triangle, where in the triangle, in this case we have 1,4 at the top, delta t at the bottom, and 3,5. You see, we have two things at the bottom. And we want delta t on its own. So, delta t is equal to 1,4 divided by 3,5. We already have 1,4 on our calculator. Divide by 3.5 is equal to 2/5, which is 0,4. Remember, you mustn't stop there. You ask yourself, what actually were we calculating? Period of time. So don't forget to give the unit seconds.